If you cannot read my handwriting, please let me know. I will try to write more slowly. Is that visible? Is that understandable? Okay, great. Okay, so we'll start out with a little review of the things that we need to remember about low mass axion searches in order to understand this. Then we'll talk about the standard quantum limit a little bit more. Again, I mentioned that in the cavity talk, but I'll talk in more detail about what that actually means. Then I'll talk about the different noise regimes. So depending on what frequency you're looking at, the noise looks very different, and so you need to think differently about how you're doing an optimization. So let me fix this. And then I'll talk about something called sensitivity bandwidth. So we talked about the resonator bandwidth. That's basically the full width half max of your resonant shape. It turns out that you can actually you can have sensitivity to axions over a wider bandwidth than just that resonator bandwidth. And that's what we call sensitivity bandwidth. Some people call it the visibility bandwidth. That can really increase the rate that you can scan over the different axion masses. And so I'll talk about how that's defined and how you can actually improve that sensitivity bandwidth. And then I'll talk about some of the current technology that we use for low mass axion sensing, which is squids. And then the future, how we're going to get beyond the standard quantum limit with something called an RQU. Okay. So first, going to review. Of course, we've seen this many times, but the signal we're looking for is an effective current. And so from this signal, we know everything that we need for the ingredients for an experiment. We have to have a magnetic field, we have to have a coupling system, and we need a very sensitive current sensor because this is so tiny. And so that's really what we're going to be talking about today, is that very sensitive sensor, that third ingredient, in order to actually be able to see these tiny signals. So what does a lumped element detector actually look like? Well, once again, we have some sort of current source that we couple with a transformer coupling to a tunable resonator made out of lumped inductors and capacitors, and then we need to read that out with some sort of amplifier, and then we can digitize that. So last time when I drew this diagram, I actually drew this part as just a squid, but you could have any kind of amplifier in your system. It just has to be something low noise. So you could equally well just substitute this out with a squid there. Okay, and then I think this is the last bit of review that I want to talk about is actually what our scan rate is. So you recall that there's some components of the scan rate that are controlled by the axion physics and some components of the scan rate that are controlled by the detector itself. And I'm going to ignore the axion physics for now, and I'll just say that our scan rate is proportional to things that control the size of our signal. So this is CPU. This is analogous to the form factor for cavities. The quality factor of your resonator. The magnetic field strength and volume. Your inductance that you couple to. And then the thing that is hurting you is the noise that is added to your system, and that is related to the fundamental temperature of your system, so the physical temperature, and then any additional sources of noise that are going to contribute to your entire noise temperature. And in particular, we use this parameter eta to talk about the additional noise from your amplifiers. And so this is, again, really what we're going to be talking about today, is how can we reduce eta in order to improve our entire signal-to-noise ratio and therefore improve our scan rate. Because as we were talking about, again, during the last lecture, you could have to scan for hundreds of years unless you improve your noise very significantly. Okay, so what is the fundamental limitation on this? Well, unless you're doing quantum tricks, you're going to be fundamentally limited by quantum noise. So So now let's talk about the standard quantum limit. So the standard quantum limit is basically the Heisenberg uncertainty principle. So the most basic version of this, right, is delta x, delta p has to be greater than or equal to h bar over 2. Now, we don't care about position and momentum, but there are lots of other conjugate variables out there. And so the ones we really care about when we're doing this signal, because we're looking for coherent signals, are amplitude and phase, or equivalently sine and cosine, right? So amplitude and phase, or sine and cosine. And those are equivalent descriptions of any kind of sinusoidal signal. You can either write it as a sum of sine and cosine components, or in terms of like a e to the I phi, right? Okay, now one thing to note is that, like I said, this is the fundamental limit on what your amplifier can do. There are lots of other sources of noise that you have to think about. So we talked about like radio stations yesterday, right? That's not something you can improve by going beyond the standard quantum limit. Also, your amplifier might just not be very good. You won't even be able to reach this, much less go beyond it. But the way we can quantify any amplifier, whether or not it's sort of quantum, is as a ratio to the like sort of quanta inside it. So let me write this. So eta, this is how we're quantifying it, is, so this is the minimum noise temperature that any given amplifier can achieve. And we're going to compare that to the number of photons. So h bar omega over 2. Sorry if that's not very clear, omega. Okay, does that make sense what I mean by this? This is the ratio to this standard quantum limit, right? This is a number of photons. Okay, and then I just want to redraw for a second what I mean by temperature. So you can, again, take any amplifier and have it as a number of Kelvin instead of a number of quanta. And so the amount of noise power over any given bandwidth, you can just describe like this. And so this can be in watts per hertz. Okay. So this is like as if it were produced by Johnson noise. Okay, so this is the standard quantum limit. You have to have at least a half a photon of noise that's added by amplifier. If you're measuring both of these components, even if I don't care about P, if I'm measuring X, I'm still going to get this additional half photon or some additional baseline of noise. I guess it's not a half photon if you're measuring X, but you're going to measure an additional half photon of noise when you're making that measurement. Now, the way you can beat this is if I really don't care about P and I only care about X, I can have all of this uncertainty be in P rather than in X. So that's what we mean when we say beating the standard quantum limit. And this has actually been done in axion experiments already. So the haystack experiment used something called squeezing, where they basically squeeze the noise into one quadrature and read out the other. And then you can also do this at sort of its ultimate limit with something called photon counting, where you're basically only measuring amplitude and you're not measuring phase. And so people have demonstrated that for dark photon experiments. They did that with a qubit readout. And they got a factor of something, I think it was like 2,000 improvement in scan rate, right? So this is a major improvement. If we're talking about 100-year scan time with something where you're not doing these quantum tricks, and then you improve that by a factor of 2,000, suddenly that's just one project for a graduate student among many projects rather than many lifetimes of work. Okay, so this is the sort of equation version. Let's see what this actually looks like when we plot it. Okay, so we can write out the different quadratures. I'll put them generically as x hat and y hat, but this could be sine and cosine or amplitude and phase. When you say that you have this sort of baseline amount of noise, it means that there's a certain area on this plot that has noise. So if you're just measuring vacuum, and I'm measuring the vacuum state, I could be measuring anything in here, right? Does that make sense? This is important. It's an area on this plot that is additionally added by noise. I can't measure vacuum perfectly precisely. I'll have some area in here. Yeah? Yeah. So these are different quadratures. So these are two different non-commuting variables. And it could be anything. So if I'm trying to measure a particle, this could be the position of the particle and the momentum of the particle. If I'm trying to measure a coherent signal, it could be the amplitude of that signal and the phase of that signal. So it could be any of those. And I'm just writing it generally for now, and then I'll get more specific about the ones that we actually use when I'm talking about the experiment. This confused me for a while, too, because people always just write X and Y, and it's just a generic way of looking at it. Yeah, you have a question? Yes, exactly. Okay. So this is if I'm just measuring vacuum, but say I actually have a signal. Okay, so that means it'll have some amplitude and some phase, or it'll have some X and some Y. And so you can think about that as some vector in this space. And then there's some uncertainty around it still, right? So this is, this whole space is the sort of quantum space that it could occupy, right? And so I'll measure some value within there. This is fine. Okay, I can see that it has some amplitude and some phase. But you can imagine, right, if I have some signal and this is the noise, you cannot distinguish this, or maybe that's not the center of the circle. There we go, that's the center of the circle. You can't distinguish this signal from nothing. And so that's the problem here. So we want to try and figure out how we can decrease this amount of noise so that we can actually distinguish this very small signal with quantum noise on it from nothing. Okay, so if we're going to do this procedure then, where we beat the standard quantum limit, we want to reduce the noise in one of these quadratures and put it into the other quadrature. Again, we're maintaining the area of this quantum noise blob, but we're just changing its shape. So you can imagine if you have some signal, instead of, actually I think there might be colors in here, that would be nice. Okay, so if you have your sort of, doesn't look very different from white. Okay, thank you, appreciate it. Yeah, I think this blue maybe. There we go. Okay, so that's your baseline noise. You can say you wanted to measure the X quadrature. You could squeeze it instead to have something that looks more like this. Okay, so you can imagine that this shape has the same area as this shape, but suddenly you now have a much more precise measurement of X compared to what you had before. Okay, and then again, if you look at this sort of small signal approximation, right, if you're able to squeeze this noise this way, and you're only measuring this quadrature, now you can distinguish this point from 0. Okay. One problem here, right, is we don't know which of these phases we should be measuring, right, because we don't know what the phase of the axion signal is. But it turns out that that's not too much of a problem. Okay, yeah, if you knew what the phase is, you'd get more precision, but nice, thank you, appreciate it. Okay, so say your axion signal is some random phase, and say I just choose to read out in X. So what I'll do is I'll squeeze an X, and now I can clearly see there's a difference here. Now, if to read out in terms of Y, you would not be able to tell, right, which signal it's in. Now, it turned out that that was the right phase to read out, right, because it's like more closely aligned with the x-axis. But if you instead read out, yay, colors. If you instead chose to read out in Y and you squeezed in Y, okay, yeah, you don't have as far of a distance from the origin, but still you can potentially improve your signal. And maybe this is not squeezed enough, so you still have like more uncertainty here, but you're still reducing your uncertainty along that axis. And if you're integrating for a long amount of time, the phase of the signal is going to change, and so you're going to be sort of averaging, and eventually you'll see the difference from the origin. Okay, does that make sense in this sort of schematic picture? Okay. No, right, because you have to maintain the area of the thing. So you can't squeeze in both directions. You can't just suddenly have reduced the area of this circle. You can squeeze in one direction and read out in one direction, and you could do this poorly. You could squeeze in this direction and read out in this direction, and that would be a bad idea. You want to make sure you're squeezing the noise into the quadrature you're not reading out. No, quantum mechanics will tell you that you are fundamentally reading out both quadratures, and you can't do that. Because, yeah. I'm not quite sure I'm following. You're saying if there's a way of reading out both or one quadrature? Yeah, so the experiment could be the same, but the sensors themselves, some are what we call, and I'll get a little bit more detail about how this actually works, but some are phase insensitive, so there's no way of distinguishing, and some are phase sensitive. And so if you want to beat the standard quantum limit, you want to read out with a phase sensitive amplifier, because it doesn't matter if you squeeze your noise, if you're still reading out both quadratures, that's useless. Yeah, that answers the question? Okay, great. Other questions here? Okay, so we have this schematic picture just in terms of two quadratures. Now let's talk about what that actually looks like if we're reading out a time-dependent sinusoidal signal. So we're reading out in terms of sine and cosine. Okay, so here I have time. And say my signal looks like this. And there's some sort of noise associated with it. So I can write this signal as the sum of a sine term and a cosine term. And so I can see how well I can do this. Okay, so the signal is the sum of these two different sine and cosine curves. So the again, if you're doing phase insensitive readout, you would have both of these would have some uncertainty. And so if you chose to just read out one of these quadratures, you would still have that same amount of uncertainty, right? But you can do this squeezing effect by basically making one of these curves have more uncertainty band on it. Excuse my sort of funny drawings. And then decrease the uncertainty width on this other one. It's a little hard to do that manually, but you kind of see what I'm saying, right? So one of these has a larger width and one of these has a smaller width. And so what I want to do is I want to be sort of phase locked to this signal so that I'm reading out and I can get a very precise measurement of this cosine term, and then I just put a bunch of uncertainty onto that sine term. And so then I can see that there's actually a signal there. Okay. All right, so once again, this is only me measuring the noise in my amplifier, right? So if my, and this is also only the quantum noise in my amplifier. So if my amplifier has a lot of additional other kinds of noise, squeezing isn't going to help. So if you want to go back to this picture right here, you can imagine that if you have sort of this level of quantum noise, you would have a much larger sort of area of additional noise added on top. Squeezing this amount, even if it will be inside this much larger additional source of noise, and so you're still not going to have any improvement, or at least not much improvement. It'll be a sub-dominant contribution. Okay, so this is the principle. Now I want to go back to the different regimes of noise, because it turns out that this can't actually always help you improve your signal-to-noise ratio because of exactly what I'm talking about here. Actually, I think I'm going to leave this one. Okay, so here we have frequency of your signal, and I'm going to call this N. So this is the occupation number of resonators in your, the occupation number of photons in your resonator. And so this is exactly what we were talking about before, right? You want to load your resonator with as many photons as possible. You're coherently ringing it up. But your resonator is also going to be rung up by noise photons. So if you think about this standard quantum limit, right, it's just adding a half photon of noise. It doesn't matter what the frequency of your signal is, it's just going to add some baseline amount of noise. So, okay, so this is your SQL line. But then we also have thermal noise in our system. So if we do our Bose-Einstein statistics, we can get a calculation for what that should be. Okay, so this is just the standard thing. And what this means is that at low temperatures, you're going to have a higher number of photons in your bath. And I think this is a fairly intuitive kind of thing, right? If you have some baseline temperature, if you have higher energy photons, there are going to be fewer of them to occupy that amount of energy, right? If you have lower energy photons, you have to have more photons for whatever amount of energy you have in your system, and that's what's defined by your temperature. So, this is on a log-log scale. It would be basically just a line. This red is not very red. That was supposed to be red for temperature. Now, where the position of this line is will depend on what this temperature actually is, right? So if I decrease the temperature of my system, I can move this line up and down. But so now we have these two different sources of noise that have two different shapes with respect to frequency. So when you're at high masses, and these intersect, if you assume that this is a 10 millikelvin temperatures, this intersection is right around, it's around a gigahertz, a little below a gigahertz. So the cavity experiments that we were talking about this morning, they're firmly in this regime, right? I showed you that plot where as you brought the temperature down, the thermal noise went below the amplifier noise. So what this means is if you can do squeezing, you can do this process where you squeeze your noise in one quadrature, you can actually reduce the total noise in your system. So you're directly improving your signal to noise ratio. As you go below this intersection point, that's no longer true. You're back in that regime where you have this wider noise blob, and squeezing is not going to actually improve your total noise performance. Okay, so at first that seems like, okay, great, you can do all those nice quantum tricks up here. What's the point down here? It turns out that although you cannot improve your signal to noise ratio, you can actually improve the bandwidth you can search over. And so this is the sensitivity bandwidth thing. So even though signal to noise ratio is not changing, you can still improve your scan time because you're looking over a wider band of frequencies all at once. Okay. Yeah. So we can label this as 10 millikelvin. And then again, so as you increase the temperature, this position is going to move. And the reason why we don't just say, oh, let's just reduce our temperature is that is technologically impossible to move much. I mean, maybe you could operate at 8 millikelvin, right? But like that's not going to help very much. Other questions here before I start talking about bandwidth? Okay. So now I'm going to draw basically what the response is of our resonator. Okay, so once again, we have frequency. And this is just the response. So you can think about this as the amount of current that you're reading out. You can think about it as the number of photons in your resonator, however you want. you're going to have different noise sources that have different shapes. So let's go back over here. So if I have noise entering my system over here, it's not seeing the resonator at all, right? Noise entering here and then being read out. There's not going to be any sort of interesting shape with respect to frequency. And so we'll just have some flat noise contribution. Now, if we have noise that enters our system here, it will be shaped by the resonator, right? It'll be either rung up if it's on resonance, or it'll be not rung up if it's not on resonance. And so you'll see this resonant shape on top of it. Now, the bandwidth of our resonator is just the full width half max of our resonator, and so you could draw some band, right? Oops, that's not very symmetric. There we go. So you can think of this as your resonator bandwidth. Your dark matter signals are also going to be entering your resonator, so they're also going to have this particular shape. So you can think of it's going to be narrowband, say, assuming that your axion quality factor is higher than your resonator quality factor, which is true for all existing experiments. You can think about it as, okay, so those are 4 examples of dark matter signals. The one that's in your resonator bandwidth has the full signal to noise ratio. The one that is way off resonance is fully below your noise, right? So this is your total noise right here. But you'll notice that this also has the same signal to noise ratio as this signal, despite the fact that it's outside your resonator bandwidth. So that's where the sensitivity bandwidth part comes in. This is your sensitivity bandwidth. It's basically the intersection point where your resonator-shaped noise hits your noise that's not shaped by your resonator. It didn't matter if you were technically off resonance, as long as you're still within the point where you're not being swamped by this additional noise that's not shaped by your resonator. Does that make sense? Yeah? Yeah, question? Yeah, okay, so this is assuming that you have a big enough signal. So it could be that you have a signal that is totally buried under here, and it would be also shaped by the resonator, but it's too low. So assuming you have something that on resonance has a high enough signal-to-noise ratio, the signal-to-noise ratio will be the same over here. If you think about this as a log-log plot rather than linear, obviously there's going to be some slight reduction, but this would be subdominant. Does that make sense? Does that answer the question? Okay. Yeah. Yeah, great. So that was just the sort of schematic view of noise that doesn't get shaped and the noise that does get shaped. But thermal noise on your resonator will get shaped. Thermal noise up here won't get shaped, right? So all of these things are contributing noise, right? The one we really care about is the noise inside your resonator, because that's the thing that's going to be affecting the signal-to-noise ratio on resonance, or rather in the sensitivity bandwidth. Okay, so it turns out that there's more than just thermal noise in your resonator, though. There's other sources of noise as well. And so if you think about, remember, there's going to be some effective noise temperature for this amplifier. Some of it is just going to be going along with the flow. It's going to be going to your digitizer. That's what we call imprecision noise for your amplifier. Some of the noise, though, is actually going to be traveling backwards because it's just emitting, right? This is what we call back action. Any noise, or I'll label this as imprecision as well. Ooh, that's a squeaky one. Imprecision. Okay, any noise that is back acting from your amplifier back into your resonator will be shaped. So you can think of this is just imprecision noise. This is just any noise that's downstream. This noise has multiple different components to it. So say this is your thermal noise. There will be another line on here that has the same resonator shape that's actually back action noise from your amplifier. Okay, so that's that's fine. Imagine we know what the total noise is for our amplifier, right? We can change where the noise is going by changing this input coupling. So if we increase this coupling, you could have more of your noise coming out as back action and less coming out as imprecision, and then vice versa, right? If you decouple your input coupling to your amplifier, you could have more come as imprecision and less as back action. That's just a fixed property. The total noise is just a fixed property of your amplifier. So you can see right here that the thing we want is to improve our scan rate. And so the way we do that is by increasing the sensitivity bandwidth. Okay, so how do we actually do that? Well, again, if we have a fixed amount of noise and we can tune where it goes, what we want to do is we want to drop this imprecision noise because that will allow us to improve this. And so we can take the imprecision noise and put it into this back action curve instead. So this is where it was before. You can imagine dropping this. Is this diagram becoming too confusing at this point, or should I redraw it? Can people see? Okay, so I dropped my imprecision noise and I increased my back action noise. So it's now at the same level as my thermal noise. And so now you can see I've extended my sensitivity bandwidth out to this wider width. And so now we've increased the rate we can scan at. Because once again, this is now going to have a higher signal-to-noise ratio, right? It's going to have the same signal-to-noise ratio as on resonance. We've just sort of allowed that particular dark matter to be seen by that same frequency step. This is a critical thing. Does that not make sense to anybody? Yeah. So what we want is to be able to scan as fast as we can at a given signal-to-noise ratio. And so by increasing this sensitivity bandwidth, we're increasing the region where we have the same signal-to-noise ratio. We're not improving SNR. This thermal noise is fundamental. But this particular dark matter signal, which before was buried partially under this imprecision noise, now is at full signal-to-noise ratio because we've increased the sensitivity bandwidth. We've dropped the imprecision noise, and now the fundamental noise is only shaped by the resonator. Does that make sense? Okay, good. Yes? If I had increased my back action noise above my thermal noise, that absolutely would be true. But if I don't increase it above the thermal noise, I'm not increasing the total noise. Again, this is a log-log plot, so okay, maybe you increase it by a factor of 2 or something, but okay. Stop me and come back to this if things get confusing as we move on. Okay, so what we've done is we've kept our amplifier noise fixed, and we've just changed the shape. If we can improve our amplifier, we can decrease that total noise, which means you can continue to decrease that imprecision noise. So that's basically what we're doing as we're getting better amplifiers, getting closer and closer to the standard quantum limit. We're just decreasing that total noise so that we can shift the same amount of back action noise to match that thermal noise, but continue to drop imprecision noise. Okay, but at some point, you're going to run into this quantum limit where you cannot change the area of that blob. There's no maybe additional outside of it, but you can't continue to do that. So that's when we need to go beyond the standard quantum limit. So I'm going to redraw this because I think it'll start to get a little too confusing. So what I'm going to do is I'm going to redraw it with the back action having 2 different quadratures. Okay, so we have this imprecision noise, we have our thermal noise, and then we have back action quadrature 1, And then we have back action quadrature 2. And right now they're the same. Okay. I want to keep dropping this imprecision noise. What I can do is I can just add my back action back to a single quadrature. So what I'm going to do is I'm going to suddenly ramp up and have a huge amount of back action in, say, this is quadrature 1, and I'm reading out quadrature 2. And that allows me to drop this imprecision noise even farther. So again, we've kept the same total noise, but we've dropped imprecision, put the noise into quadrature 1 without affecting our signal to noise ratio because we're only reading out in quadrature 2. Okay, so now suddenly, again, we've improved our sensitivity bandwidth. Same signal to noise ratio, but we're reading out faster because each step has a wider frequency band. Yeah? So the imprecision also would have some quadratures. We just don't care about the quadratures of the imprecision. All we care about is just dropping that imprecision noise. Other questions here? Okay. So that's how this works. Now I want to talk about some real technology that we can actually use. So right now we use something called a squid in order to make our experiments work. This technology has been around for quite a long time. Actually, the Nobel Prize this year was John Clark was one of the people who won it, and he did some of the really seminal work on squids. And he's also done work on developing squids for a bunch of different axion experiments, including ADMX and also DM radio. So what is a squid? This is the basic format. So you basically have a loop of superconductor with 2 Josephson junctions inside it. This is a DC squid. You see some other types of squid. So there's RF squid where you only have 1 Josephson junction. We'll just ignore that for now. We're just talking about DC squids. This is fundamentally a magnetic flux measurement device. So basically what you do is you send some signal in and you couple it via an inductor, and then you end up with magnetic field inside this loop. When you have a superconductor, there's going to be a supercurrent that is induced on a loop that's going to try to cancel out any induced magnetic flux in that superconducting loop. So one thing to know about magnetic flux in superconductors is that it is actually quantized, and the magnetic flux quantum is just h over 2e. You can think of this 2e as basically, oh yeah, sorry, go ahead. Yes, absolutely. Great, thank you for stopping me. So a Josephson junction is basically a sandwich of a superconductor, insulator superconductor, or a superconductor, normal conductor superconductor. And so in real sort of wafer, you basically have a piece of superconductor, then you might have like an oxide layer, that would be your insulator, and then you have another piece of metal on top of it. And in a classical system, you would have no charge flow here, but because we have a quantum system, you can have tunneling across this junction. And so you can either have Cooper pairs tunneling, or you can have quasi-particles, basically single electrons, tunneling across this junction. Yes? Yeah. I think maybe on Friday I'll show some pictures of some actual Josephson junctions because we use them in qubits as well. But yeah, so the way you usually make this is basically, yeah, you have some sort of wafer, you deposit metal at different angles, and then in between depositing this piece of metal and this piece of metal, you add a little bit of oxygen to the tool that you're using to make this, and that'll oxidize just a thin layer on top of it before you put your other piece of metal down. And so this can be extremely thin. We're talking about like nanometer scale thin. And then if you're looking sort of top-down view, there'll be like a piece of metal and then sort of an oxide. 2 different pieces of metal and there's an oxide layer in between them. Yeah? Yeah. So basically, Josephson junctions give you, am I going to talk about it in this lecture or the next lecture? I can't remember. I think I'm going to talk about it. I'll talk about it later in this lecture. Yeah. So Josephson junctions have very weird properties. There's like different effects that happen. There's like a DC and an AC Josephson junction effect. Basically, you can think of this as a nonlinear inductance. And so that gives you all sorts of cool things. So I'll talk about it in the context of RQUs, which are these devices that we can use to evade the standard quantum limit. I didn't want to talk in too much detail about squids themselves. One, because they're sort of classic quantum technology, but also because they're extremely complicated in how they actually function. So I'll give a few details, but not very much. Okay, so that's the brief sort of nanofab details. Okay, so like I said, flux is quantized inside a superconducting loop. And so basically what's going to happen is you're going to have currents that are set up to try to cancel out this magnetic field. And then as you reach individual flux quanta, basically a single unit of flux will enter that loop. It'll reset. And then as you add more magnetic flux, more currents will be induced. And so the way you actually operate these is you add some sort of bias current or bias voltage, and then you read out the opposite. So say if you bias it with a current, you'll read out what the voltage is across this device, and depending on how much flux has entered this loop, it'll change the voltage across these junctions. These devices have been used to measure extremely low magnetic fields, and they've been around for a while, so they're now in use for all sorts of like real-world commercial applications. So I found on Wikipedia that they can measure down to 10 to the minus 18 Tesla. So this really gives you a sense of the different sort of scales that are involved in these experiments. We're talking about 10 Tesla fields and 10 to the minus 18 Tesla for signal. So like I said, you can think of these as basically a nonlinear inductance. If you look at an individual Josephson junction, the sort of equivalent picture of it is you'd have sort of a bunch of different elements. And here, you can think of it as shunted by a resistor and a capacitor, sort of like effectively. In real life, you actually have to add all sorts of shunts across these things to make these things act in sort of an operable linear way without a bunch of hysteresis. So like I said, I'm not going to talk in great detail about how squids actually work. There's many textbooks written about this. Okay, so squids have all of this sort of stuff, like resistive shunts and things like that inside them, which means there is going to be additional noise. They're not going to be able to get down even to the standard quantum limit. But if you could, why do you think you wouldn't actually be able to go beyond the standard quantum limit with these devices? Just looking at this sort of how we're reading them out. We have a current bias, we're reading out a voltage signal. What are the things we need to get beyond standard quantum limit readout that we were just talking about over here? Yes. So technically you could read out one quadrature signal, but can you use this to affect? No, yeah, exactly. There's no way to basically change what the quadrature is of the noise that you're putting back in, because they're just inductively coupled. There's nothing fancy going on there. Okay. I put some notes in here about some of the applications because I went down a Wikipedia rabbit hole when I was looking for the amount of field they can reach. So I'll read out a few of them because I think it's interesting. They're used for oil prospecting, mineral exploration, geothermal energy, MRI, measuring neuron activity, and a lot of times they're also used for measuring like properties of materials in just commercial systems. You can just buy a system that comes equipped with squids. And so for the original abracadabra 10 centimeter experiment and for DM radio 50 liter, you can actually just use commercial off-the-shelf squids for these devices. Now, those won't have the best noise performance, so as we scale up for more sensitive experiments, we're designing our own squids to really reach their maximal performance. But long term, again, we want to go to something where we can evade the SQL. So, I do want to have one note before I move on to RQUs, actually. I want to just talk about how we cascade squids. So in the last talk, you saw how basically you can cascade different amplifiers of different gains, and we do the same thing with squid devices. So if you think about you attach your resonator, There's going to be some first stage squid that will give you a small amount of amplification and also a small amount of noise. And then you basically cascade this with arrays with a bunch of squids. And this allows you to get more amplification, et cetera, et cetera. And then you could just feed it into a normal preamplifier and then read it out with your digitizer. And so one thing that's kind of fun is we actually use the same kinds of squid arrays that you use to read out cosmic microwave background experiments as our second stage, though. For our first stage squid, as we're trying to get more sensitive, we'll be designing this as a very special sort of weakly coupled squid. Yeah, so these CMB experiments, their first stage, instead of being a squid, is like a transition edge sensor. And then you can read out the signal from a TES using squid arrays. Yeah. So the best that we can do theoretically with this style of squid, where we do something fancy on the input and then something more standard for our different stages of gain, is a factor of a few above the SQL. So for our projections for diameter meter cubed, we use eta of 20, but that's being pretty conservative. We think we can get down to something like 5 or 10.
Sorry, I think I missed. I thought this was like get the classical. How does putting a bunch of squids allow you to choose quadratures?
This is not going beyond SQL. This is above. It's eta of.
Above, not
yeah. So the standard quantum limit is eta of 1. Yeah. So we're talking about like 5 to 20. Oh yeah. Above is worse. Okay. Okay. So again, this is sort of standard quantum technology. It's kind of funny that we can say that. Okay, and so now I want to get to radio frequency quantum upconverters, or RQUs. And so disclaimer here, I don't actually work on developing RQUs. Some of my collaborators do. But we are planning on implementing these for future versions of DM radio. So I'll do my best talking about this particular technology. Yeah, here I can write that out. Okay. Upconverter, yes. Okay, so let's talk about the name, I guess, first, because that gives you some details about how these things actually function. So the upconversion part is basically saying we have kilohertz to megahertz signals in our detector. There's a lot of technology for working at the gigahertz. That's where the Wi-Fi band is, which has led to a lot of like qubits are also in the gigahertz. A lot of this cavity technology is in the gigahertz. What if we can use that technology in order to read out kilohertz and megahertz signals? So what we are going to do is we're going to take those kilohertz to megahertz signals and we're going to upconvert them into gigahertz signals that we can then read out. Okay, so let me go ahead and draw what this actually looks like. So basically you're going to have some sort of transmission line. Then we have a circulator from the last lecture. Okay, so we're going to have some sort of pump tone, and then we're going to read out on this side. And in the middle, we're going to couple this to a resonator. Where this has some sort of tunable inductance. So we have a pump tone. Sorry, I forgot to draw the signal. The axion signal is going to come in, and we're going to couple this in via an inductor again. Okay, so we have an axion signal. It's going to enter this resonator. The critical thing here is that is going to change the inductance of this resonator. And the reason we want it to change the inductance of this resonator is as we send this signal, this pump tone, down this transmission line, it's going to interact with this resonator before we read it out, and it's going to go through this mixing process. And so you're going to have side bands generated on this tone based on its mixing with this lower frequency signal. And so as you add flux to this resonator, it's going to change the position of those sidebands because that'll change the resonance frequency here. Okay, so I want to talk, before I talk about all the sideband details, about how this part actually works. And this comes back to the Josephson junction piece. How can you make a tunable inductance just by changing some magnetic flux? Go over here. Okay, so this is the part about the AC and DC Josephson junction effects. So if you have this structure where you have a superconductor, insulator, superconductor, you're going to get these sort of strange things where you have the current, there'll be a current induced across it, dependent on the phase across your junction. So in a superconductor, you're not thinking about the voltage across it, right? Because it's superconducting, there's no resistance. You're thinking about the superconducting wave function. And so depending on the phase of that wave function across this junction, you're going to get a DC current induced. And this here is the critical current across that junction. So if you drive a lot of current across the junction, it will no longer act like a superconductor. But if you drive current below this critical threshold, it will be a supercurrent. Okay, so this is the DC Josephson effect. You also have this AC Josephson effect, where if you have a voltage across the junction, you're going to change the phase of that superconducting wave function across it as well in a time-varying way. Okay, so we can use these two facts and understand, sorry, what is it? Two underscore. This is 2E, so this is the charge of your Cooper pair.
It's not underscore.
No.
Okay, that was what I was
Yeah. Time varying voltage over H bar. Yeah. Okay, so let's use this and see how you get a nonlinear inductance, a flux-controlled inductance from your Josephson junction. Okay, so the first thing I want to do is I just want to plug in, remember, we know that we have this flux quantum. We can just plug that in. And so we can see that, actually first I'm going to do the chain rule and then I'll plug it in. So basically we want to see what the time-varying current is across this junction. So this is going to be so we need to figure out what this is. We can plug this in. Okay, pretty simple. And then is that di dt. Okay, so here I've plugged in this formula for the flux quantum, and here I've just taken this derivative of I with respect to the phase. And then I want to figure out what the voltage is across this junction. Okay. So the voltage across the junction then is just going to be the change in current across the junction with respect to time times okay, so you'll notice that this looks like an inductance, right? Because you have a voltage times a change in di dt, a change in current. That is, you can identify as an inductance that is a function of this phase. Okay, and then you might also, this is a tradition, you can call this the Josephson inductance. And this is a fundamental thing that shows up in a lot of places. When you're talking about qubits, this is a critical parameter. But basically, you have an inductance that's a function of the phase across the junction. And so if you add flux, to some sort of like loop, you can change what the current or voltage is going across it, and that will change the fundamental inductance of this structure. Does that make sense? Questions there? Okay. So going back to this picture, we now see that we have a tunable inductance dependent on the flux from our axion signal. And so we could just substitute this structure in for that amplifier right there. The result of this is, like I said, you're going to see some sidebands. So I'll actually leave this picture still here. So your tone is going to be coming in at that pump tone. You're going to do a mixing process. We're going to mix this omega A frequency signal with your omega pump tone, and you're going to end up with sidebands. Right here. And so depending on what the frequency is of your signal, you'll change the position of these sidebands. And depending on what the amplitude is of your signal, you'll change the amplitude of the sidebands. Okay. This has actually been demonstrated with an experiment already. So they built these structures, and they were able to demonstrate this. Now, I've left a lot under the hood as to what this part actually looks like. I've told you you can do it with Josephson junctions. In fact, you do it with something that looks like an interferometer of Josephson junctions. And so you can have different amounts of flux going into these different loops, and that will allow you to sort of carefully control what the inductance is going to be. And I'm not going to go into the details here, but that's the basic picture. Okay, so maybe I'll just mention also that as a part of this is not the only thing. You're still going to have to do amplification in here. So you'll have some preamps along the line. You're still going to be stacking the gains of different components. Okay, so I've shown you that you have something now where you can take a low frequency signal and you can turn it into a high frequency signal. So you now have omega p plus or minus omega A as the signal that you're looking for. And this allows you to use all of these nice sort of Wi-Fi band components. But I haven't told you now is how you can actually make this phase sensitive. And so that's the really critical piece that we need in order to go beyond this standard quantum limit. I guess, are there any questions here before I start talking about how we can make this phase sensitive? Okay. So what you can do is you can actually modulate the pump tone that you're putting in. So you can imagine, basically, you have some high frequency signal you're putting in, but instead you modulate it with an envelope. And so now this frequency is that gigahertz frequency, but this envelope tone is a megahertz or kilohertz envelope tone. So what we're going to do is we're going to match this frequency with the frequency that we're looking for. So this is this like omega A envelope. And the reason for this is now we have something that we can try to match the phase with our axion signal. So I should have left that same picture up from earlier when I was showing you basically the sine and cosine components. But you can imagine, right, if you have your actual signal that has the same phase as this, you're going to get maximum amplification. But if you have it misaligned, where this is, right, you're going to have less amplification of your signal. Because right here, when you're driving at this moment in time, this pump tone is going to be 0, and so you're not going to be getting any sort of additional sidebands on top of it. Okay, so this has also been demonstrated that you can do this phase-sensitive amplification. And so the way that this actually looks So this is the phase of your signal versus the power. You get something that looks like this. And so here, this is in dBm. So you can get an actual 50 dB of difference between when you're in phase or out of phase with your signal. Good. Decibels. Oh, did you have a? Oh, sorry. Okay. So decibels are just a way of quantifying a signal. So this is basically a power measurement. Let's see if I can get this correct. So it's a log power over power out, power in. There's like a 2 in here somewhere. Anyway, let me just give you an example. So basically, minus 3 dB is half of your signal. Minus 20 dB is 1/100th of your signal. So what this is saying is if you have a 50 dB difference, it's 10 to the minus 5 in power. So this is a huge difference. So we have a lot of amplification here and 10 to the minus 5 lower amplification here. And so that, how much you can change your, how much you can get phase sensitive amplification is, sorry, you're making a face. Did I do something wrong? Oh, it's not quite. It's between 40 and 50. So I wrote 80 on the plot, but maybe that's there we go. It's almost 50. Yeah. Thank you. Yeah. Good subtraction. Yeah, so basically you want to have as much difference between how much you're amplifying your different phases as possible, because that's going to tell you how much you're sort of reading out one phase versus the other, right? Ideally, you would have 0 measurement in one phase and 100% measurement in the other phase. But in practice, that's hard to do. So you want to have this difference be as much as possible so that you can do this sort of phase-sensitive measurement. Okay, so that's how you get the phase-sensitive part of it. That's how you can read out certain phases. But once again, I didn't tell you how you can put back your noise into the other phase. That's the second piece that's really, really critical. So going back to this picture, it turns out that you can actually get this automatically, which is one of the things that's really cool about these devices. So if you think about when you're actually amplifying your signal, you have stuff coming out and being mixed and adding in. When you're thinking about the signal that's being put back into the back action, the noise that's going back into your device down here, it's one is being reflected and the other is not being reflected. That's the critical thing I'm trying to say. So basically, when you're doing this measurement, you're reflecting off the resonator. When you're going into it, you're not reflecting. It's a transmission measurement. And when you have a reflection, you can get that phase shift. So now we are automatically getting this 90-degree phase shift between the noise and the signal. So that's the sort of magic of RQUs. Not only can you read them out in a phase-sensitive way, but you're automatically putting the noise into the other quadrature of your signal. Okay, and then, oh yeah, go ahead. Yeah, so you're doing this wave mixing process, right? So if you don't have a wave to mix with, which is effectively what's happening right here, then you're not getting this up conversion, you're not reading it out. So if you're in phase with it, you have this mixing process. If you're out of phase, you're not mixing with it.
So the in phase is peaks, or is that just not the right picture for an in phase mix?
So I was sort of trying to draw here, like out of phase is this, right? So it's maximized when you're at the node and minimized when you're reading out maximally.
It's both. I see, it's both the readout and the inputting this power into the actual system.
Right, exactly. Yeah. So if your axion happens to have a phase that is a phase that's matching the pump envelope phase, then you are reading out maximally. If your axion signal has a phase which is maximally out of phase, 90 degrees off, then you are maximally not reading out your signal. Yeah. Does that follow for everybody? Other questions here? Okay. So the pieces that we've done, we have an amplifier, which I haven't proved to you, but I've told you that it's a low noise amplifier. That's so that we actually care about doing these quantum tricks. I've shown you that we can read it out with phase sensitivity, and I've also told you that we can have our back action noise go in 90 degrees out of phase. And so those are all the pieces that we need in order to do this back action evasion. Oh, sorry, one more piece is that we want to be able to tune this input coupling. And you can do that by just changing the strength of this transformer coupling here. Okay, so all of this has been done except for the back action part. So the part where you actually measure how much you're putting your back action noise back in, that hasn't happened yet. We need to couple a resonator to its input, and then we can start actually implementing these into axion experiments. So I just want to talk a little bit about the amount of beating SQL we actually need. So it depends on how well we do on the other pieces of R&D. But if you think about an experiment like GUT, I told you that we were trying to aim for magnetic fields that are somewhere in the range of 15 Tesla with volumes that are somewhere in the range of 10 meters cubed. And ideally, we have an integration time that's something on the order of a grad student, so 5 to 10 years. Hopefully, the grad student isn't 10 years, but we're talking orders of magnitude here. If we can achieve quality factors of something like 20 million, which we're 1 order of magnitude off right now, we've done 2 million, then we need an eta of minus 20 decibels. So 10 to the minus 2 improvement compared to the quantum noise, quantum limit. And this gets you a scan time of about 6 years if you do the sort of rough napkin math. So like I said, we already showed that we were able to get a sort of difference in the phase that you read out by about 50 decibels. That's not enough. Once you start coupling it to a resonator, you're going to be adding additional sources of loss and things like that. So this is the direction we're heading in, but it looks promising. So I was thinking that Katerina might talk a little bit about squeezing, but that was not part of the slide she gave. So I just maybe just want to mention this whole thing about back action evasion is the same idea, but a different implementation than you do for cavities. So for cavities, we're in that regime where you can actually improve your signal to noise ratio. And so what you need to do is you basically inject the vacuum of your cavity with noise with a single phase, and then you read out with the other phase. And people can do this with, I think they've done it with JPAs, is what they've done for Haystack. So they're using those parametric amplifiers, which are parametrically amplifying one phase, right? Because if you have the swing, you're basically pumping it in one phase, and then you're not reading out the other phase. And so you can basically pump your cavity with the opposite phase that you're reading out in. So that's the sort of basic idea there. So I'm a little bit early. I thought I might show a few pictures of some of these devices, and then we can wrap up and call it there. So do you know how to connect to the, yeah? In terms of phase? Yeah. So if you're only reading out over one coherence time, yeah, you could get unlucky. Like if you think about the this quadrature plot that I showed you before, oops. If your signal is here and you're reading out along this quadrature, you get really unlucky. But probably there's going to be some component is lined up. So maybe you're like this. So you have some component that you're reading out, but maybe it's harder to distinguish from the vacuum. But if you integrate for a long period of time, the phase is going to get moved around, and then you just pick a phase, and then you read out for an extended period of time. No, you read out in practice for longer, yeah. And you just start to add incoherently. Yeah. I guess are there other questions before we show some pictures of devices? Okay. Yeah. Can you connect to the Zoom? Yeah, I can connect to the Zoom. We can just show it here, that's fine. Okay, so here's a picture of what some of these devices actually look like. I showed you the dilution fridge infrastructure already, so we have all these different plates. At the bottom of the coldest plate, you basically will have some sort of bracket that will get this device cold, and then you have a package which holds all of the electromagnetic fields out of your device. So what you're seeing right here is a box. This is a metal box that will hold, it's like basically a Faraday cage, and then inside it you have a printed circuit board that you mount a chip to. Actually, I'll use the laser. Yeah, so there's actually a scale right here. So this is 3 centimeters across here. So it doesn't, the size of your chip is sort of dependent on what the packaging is and what process you have. Often chips are something like a centimeter by a centimeter, give or take. Let me see if I have any pictures of the devices themselves. This might be harder to find, but you can't really see it. Basically, there's a transmission line going across. So these are SMA connectors. So you'll have an RF tone going in and out. Then here, there's a transmission line connected to this. There's the low frequency resonator down here. And then you have some wires that you basically connect in at the bottom that will have your Axion signal. And so this is the sort of standard packaging you see for a lot of these different kinds of devices, unless you can actually zoom in on the chip itself. And so I'll show some pictures on Friday, which show some of the qubit devices all nicely packaged, and you can see what the junctions look like themselves. Okay, so I think maybe we'll just call it there a little bit early, unless folks have other questions about our QUs. Yeah.
So I think I actually already asked this
Mhm.
correctly at some point, but I forget the answer. So in the end, just naively, we talk about all of this, SQL stuff. It's related basically to the fact that we're measuring these quadratures and, we're using that, blah, blah, blah. But there's also kind of a separate, it feels like there should be a separate limit, which is just, you should never be able to measure less than 1 photon, right? Like if only half, if there's the probability that, the probability to get 1 photon is less than 1/2, then you should never be able to have a measurement that gets a signal more than 1/2 of the time. And this is not a thing we really can see from this whole formalism, right? Like right? Because for photon counting, this is the limit, right? But here it's not something that we really see. Is that the right way to think of it?
Yeah, so fundamentally we're measuring many, many photons. It's just I'm not sure if I'm quite.
So I'm saying, like, let's say you did the squeezing, and then you tell me, okay, I did a 10 to the 10 dB squeezing. Wow, amazing, right? So in principle, should be able to measure enough signals that are not really there because, again, the dot meter has created less than a single photon. But if you just multiply your sensitivity by like 10 to the 10, you're suddenly going to think, oh, I'm going to measure something, right? It feels like there's kind of a separate additional noise that is usually way, way too small for us to care about. But maybe it is the same noise. That's what I'm trying to say. It's really kind of hidden in here is the fact that there has to be at least 1 photon in the system, or is it just really kind of a separate thing that is usually just not?
We're not photon number limited. We have lots and lots of photons. It's just that we have lots of noise photons also, right? So we're not actually fundamentally improving the number of noise photons in our system. We're just improving how wide of a band we have a certain number of signal photons compared to a certain number of noise photons.
So I'm saying, but can you see from this calculation the fact that there are multiple photons here, or is it just that we know that there are so many photons here that there's no need to worry about just writing down how many there are and making sure that we're not below the single photon limit?
Yeah, you can't see it here. I think you could probably see it from that plot that I showed with the thermal noise and the resonator occupation number. I didn't put any numbers on that plot, but you're talking about 10 to the a lot. I can see if I can find the numbers from my plot.
Of this thing, we need to make sure that it's always bigger, much bigger than 1, and then we're fine. That is the way.
Yeah, right. So if I just quickly draw this again. So this is 1, right, because that's the standard quantum limit. If we're talking about kilohertz frequencies, this is like 10 to the 5. Lots of photons.
Wait, but then if you go beyond the SQL, you go beyond the number 1 in terms of the number of photons in the...
Right, this is being pushed down.
But if the documented deposits like a quarter of a photon, right, you should not be able to measure.
So, but think about how much energy so it's depositing a certain amount of energy, which up here is very few photons. Down here, it's still many photons, right?
But so you could never go down there to the right.
Here, right, like if you're over here, you're starting to have fewer and fewer photons. So for bread, for example, where we're talking about milli-eV photons, when you do a calculation of sort of a reasonably sized detector, you're talking about detecting 1 photon per day.
Okay, so
But down here, we're talking about many, many photons per second. Yeah. Yeah. Yeah, and so then for bread, you're starting to talk about like low threshold photon counting, just like you are for particle dark matter detection at low thresholds.
But then squeezing really wouldn't help you, right? From the perspective of there's just a photon, it doesn't matter how much you squeeze.
Right, yeah, so this is actually really a good point. So if you're squeezing, there's different ways you can squeeze. So if you think about the picture I showed you before, you have some blob that you're squeezing along one quadrature. A different way you could think about doing it is squeezing like this, where basically you can think about this as counting the number of photons. You're thinking about an amplitude of this vector, you're not thinking about the phase of this vector. And so that's fundamentally what photon counting is doing, is you're basically going from this to now you have a circle around your thing of infinitesimal width, and you're just counting the number of photons with 0 measurement of phase. And so that's how you do better at these highest frequencies, is you photon count. That's the best you can possibly do.
So in the end, the expert plus p squared will really tell me that, you know, squeeze however much you want, but expert plus p squared is always limited to a certain quantity.
Yes. Yeah.
All right. There are no more questions.
Okay, great.